Name of this course is Theory of Computation, and let us spend a little time to understand the scope of this course. Now, we have the word computation in the title, and it is saying that our course is about the theory of this entity called computation. Now, when we talk of computation today, clearly what we understand as computation is that you write some programs and you run the programs on computers, and then in that way you carry out a computation. So, fundamental activity behind computation, or the way computation is carried out, by executing programs. So, what are programs? Let me write this term, which we are all familiar with. Programs. And in a way we can say that our theory is about programs, right. There can be various theories. I need to now say clearly specifically what we mean by our theory that we will discuss here. But again, if we think of the word program, we know there is something fundamental behind this term, even more fundamental, because after all a program is nothing but an algorithm expressed in a programming language. So, we can say programs express algorithms. And you see, already we are making an abstraction in this, that we are saying that programs express algorithms. So, more fundamental notion than program is the notion of an algorithm. So, going back again, what we can say that our theory is about theory of algorithms. Right? Theory of computation, theory of programs, theory of algorithms, all more or less denote the same thing in our context. What are algorithms for? We all know that, but let us enunciate clearly. We know that algorithm, what it does is it computes, or it gives us a recipe for computing an input output mapping. So, let us again write this, an algorithm is a recipe for carrying out input to output transformation. Okay. This seems obvious enough, that when I have a program, it is executing an algorithm, and what is that algorithm? That algorithm is a finite, effective, step by step process or description of a process, which we are calling a recipe, more familiar term, for carrying out a transformation of the given input to an output. Another way of saying this would be that an algorithm tells us how to compute a function. So, you see, if I write like this, a recipe for carrying out input to output transformation. So, in picture it will be like this is an algorithm, and as we know that it tells me for a given input how to get its output. But then we can see this as telling me what is the output for, let us say, the input x. If I call that output, if I term that output for x as f of x, then we are dealing with an even more fundamental familiar concept, is that of a function, right. So, as you know, a function f is a mapping from some domain to some range, and in this case the domain is the domain of all inputs and the range is the range of all outputs for a specific function, right. You may have an intuitive understanding of a function, right. You may have an idea what the function should compute. In other words, given an x, what f x should be, but that is not enough for actually obtaining, given an x, the value f x. For that, what we say is that we have to give an algorithm to compute that function f. So, we can say that an algorithm computes a function. Again, that is kind of very straightforward, simple understanding, right. Every algorithm computes a function, right. So, let us write this here. Every algorithm computes, or I should have said tells us how to compute a function. The distinction should be clear between algorithm and function. We all understand function is an abstract notion which tells me that here is this mapping between input and output, domain and range, and algorithm is telling me how to obtain the output for a specific input, right. In other words, we are using the word computes in that sense. Now, I can say basic goal of our theory is to figure out for what functions we can have algorithms. Now, that might sound a little unfamiliar. We may think that if we can dream of a function, if we can define a function, if we can in some way tell somebody else about a function, then that itself should be an algorithm, but really that is not the case. For example, let me provide a very simple illustration. Consider this function which is prime, right. This takes a number. So, let us say, so my domain is the set of numbers and the range is yes or no, and by that what I mean is, supposing I say is prime and then apply it on a number, then it is going to be, the output is going to be, or the answer, the value of this function on the argument n is going to be either yes or no. And now, let me define when I want the answer to be yes and when I want the answer to be no. So, let us say it should be yes if n is a prime, the number n you have given as argument is a prime, and it should be no if n is not a prime, right. So, you have defined this function But you see, clearly we are not saying, this definition itself is not telling me, given an n, how to actually come up with the answer and the right answer. And that would be, as you know, and you have surely written a program to compute this function, you will have to give an algorithm which will tell me how to, given an argument n, which is a number n, how to figure out whether it is a prime or not. And that how to should be expressed in terms of simple operations which can be carried out on a computer, right. So, these are all we know. In other words, we would like to write a program to compute this function. So, you see that underlying that program, that algorithm is computing a function. So, coming back, what we are trying to say, that it may be possible to define a function, but the definition of the function does not immediately point out in all cases to an algorithm to compute that function. If that is the case, then at least you can now see that there is a possibility that I may be able to define a function, I may be able to describe what the output should be without having an idea how to obtain the correct answer. Although we have not possibly encountered such situations in our programming experience, but it might surprise you when I tell you that actually it is a fact that for most functions there are no algorithms to compute. In other words, if you think of the class of all functions, then only a tiny fraction, only a tiny subset of these functions admit algorithms to compute them. And this is something which we will be able to prove, which we will be able to demonstrate in our theory. So, in other words, let me say a primary goal of our theory is going to be to figure out which functions can admit or will admit algorithms to compute them. The basic goal of our course that we are going to go through in this series of lectures may say as, it is to identify the class of functions which admit algorithms to compute them. So, what we are saying is that there are some functions which are of the kind that for function f there is an algorithm to compute f, right, and there are some other functions rest do not admit any algorithms to compute them. So, in this class of functions, that if you give me an input A, then I will be able to tell you by carrying out, by computing the corresponding algorithm for f, what the value of the function will be on the argument A, whatever be the argument. But in this case, it may be that for some inputs I will be able to give, but there may be inputs for which I will not be able to tell you what the output is. In other words, I will not have an algorithm in general to compute that function. And as I said, that most of the functions, unfortunately if you like, they fall in this class, that they do not admit any algorithm to compute them. So, at the end of the course, in principle, you should be able to not only have examples which are very clear and which are in a way important, of functions for which we will not have any algorithms. We should be able to prove that such is the case with those functions. And in principle, again, we will have the knowledge of the techniques to demonstrate that a function does not admit any algorithm to compute it. And that, as I said, is going to be at the very end of this course. Now, the way we look at this problem, although this is the fundamental thing, this is our basic goal, is to identify the class of functions which admit algorithms to compute them, but you will see in the course actually will not talk about functions. Instead, we will talk about a problem which is kind of related, and I will have to show you the relation, and that problem is called the membership question. Given a set and given an element, whether that element is a member of that set. Okay. So, this is the question that will engage us for most of the course, and let me clearly explain what that question is. So, let us understand what this problem is, set membership problem. It's actually very simple to state. It's a very general problem that you have some set S and our problem is that given any A as input, to decide if A is a member, is an element of the set S. Okay. So, very simple, right? There is a set, in some way we understand what is that set, and now you give me some element A, and we would like to know whether this element belongs to the set S or not. Now, as I said, all the time in this course, we will really be talking about this problem. What we will do is, we will be able to show various kinds of algorithms, not the way you study in algorithms course, but through various models of computation, the classes of set for which we can carry out this problem. Now, what is the connection between set membership problem and the basic goal that I had talked of here? You see, if you think of a function f, then remember that we said that function f, notationally we always write like this, that a function f is a mapping from some domain to some range R. Now, you might know that there is a very natural set which is associated with any function, and that set is called the graph of f. Right? And that graph of f is a set, and what is that set? That set is a set of tuples A, B, such that f of A is equal to B. Okay. Now, the point is this, that with every function f, we can associate such a graph. And now, suppose we cannot decide, we cannot give an algorithm to compute or to carry out or to solve the set membership problem of graph of f. So, let us write it down. Suppose we show that there is no algorithm to solve the set membership problem for the set graph of f. Remember, this is a set, and as we said, this particular set is defined like this. Suppose we show that there is no algorithm to solve the set membership problem for the set graph of f. Then we can conclude that there is no algorithm to compute f also, that there is no algorithm to compute f. So, what I am saying is that if we show that there is no algorithm to solve the set membership problem of graph f, then there is no algorithm to compute the function f itself. And this is quite easy to see, and we can very easily prove the equivalent contrapositive statement, in which we will say that if there is an algorithm to compute f, then there is an algorithm to solve set membership problem of graph f. So, if you have an algorithm to compute f, right, then if somebody gives you this tuple a b now, and you have an algorithm to compute f, then what you can do is look at the first argument and compute f of a using the algorithm for computing f. So, let me write this. Suppose there is an algorithm to compute f, then for a b given as input, we compute f a using the algorithm for computing f, right. Somebody has given you the algorithm to compute f, so you use that algorithm to compute f of a. So, a is what? The first argument of this tuple. And now, supposing b is f of a, then of course, a b this implies actually B equal to f of A if and only if AB is a member of graph of F, right. So, therefore, using the algorithm for computing F, I can solve the set membership problem. The set membership problem was given AB, check whether this tuple is a member of graph of F. This tuple is going to be a member of graph of F if and only if FA is equal to B. And now I have an algorithm to compute F, and therefore, clearly I take the first argument, I compute f of A, check whether B is equal to f of A, and then I can answer whether AB is a member of the set graph of F. So, therefore, this statement we have proved. It is so easy, right? Now, if I can show, therefore, that there is no algorithm for computing there is no algorithm to solve the set membership problem of graph F, then I have shown that there is no algorithm to compute F. And this is the reason you see that a function which is not computable, we will be able to get to that fact by looking at the graph of that function and proving that graph of F is something, is a kind of set, is a set for which I have no algorithm to solve the set membership problem. Now, what does it buy? Instead of functions, then I can talk only about sets, and sets are more fundamental and in a way simpler objects. And therefore, the theory, at least notationally, becomes simpler, although it manages to show the existence of functions for which we have no algorithms to compute those functions through the study of some kind of sets. And this is the reason most of the in fact entire course will concentrate on sets and their membership problem rather than functions. In fact, although that is the basic goal in our mind, because we would like to talk about programs and whether or not we can have a program to compute certain things. You will see, in fact, that this problem is not something we tackle in its generality. What I mean is that the kind of sets for which we will consider set membership problem, these sets are going to be very, very special kinds of sets. And what are the sets for which we will consider set membership problem? See, these sets are, so let me write it, our sets are going to be sets of finite strings. Okay. So, let me explain these terms. And to talk of strings, I need to first talk of alphabet, and to talk of alphabet, I need to talk of symbols. Now, so let me first use the term symbol. What is a symbol? We are not going to define it. Only thing we would like to say about symbols, that they are as you know them. For example, 0, 1, these are symbols, right? Similarly, A, B, these are symbols, right? And what another term that we are going to use is called alphabet. So, an alphabet is a finite set of symbols. As an example, this is an alphabet, right? There are two symbols 0 and 1. The set comprising of these two symbols is an alphabet. Also another example could be A, B, C, D all the way through Z. And you can, of course, give many other examples of finite sets which are made up of or which comprise of symbols. Okay. And now, let us just consider this set A, B, C. So, this is an alphabet because this consists of, it has three members, three symbols A, B, C. And again another familiar term is a string over these symbols. So, what is a string? String is we just write an ordered way, we write these symbols one after another up to some point. So, let us say B, A, B, C. This is a string over this alphabet. So, we can formally define all this more carefully, but this notion is so simple you get it immediately, that this is a string in which the first symbol is B, second symbol is A. So, there is a notion of ordering. We can talk of first, second, third, fourth, fifth, and also there is a notion of length, because this has, you can see its length is 5 because it has 5 symbols, right? And this is also a finite string. There could have been infinite strings over the same alphabet, but we will restrict ourselves to finite strings over an alphabet. Now, suppose sigma is an alphabet. Then sigma star denotes the set of all finite strings over sigma. Okay. Now, supposing my sigma is 0, 1, suppose as example I take sigma is 0, 1, then what is sigma star? It's not difficult to see. So, what are the strings over this alphabet? They are going to be binary strings. And we said sigma star denotes the set of all finite strings over sigma, and this is the binary alphabet. So, therefore, sigma star in this case is going to be the set of all finite binary strings. So, as we are saying that consider the binary alphabet which consists of just two symbols 0 and 1. In that case, the sigma star is going to be the set of all finite binary strings, right. By this, what do I mean, the finite binary strings? You know, we don't allow in sigma star to have an infinitely long string, but all strings whose lengths are finite, they will be members of sigma star, and those are the finite binary strings. So, there is really no upper bound on the length of strings which we have in sigma star, but at the same time every string, any particular string that we take in sigma star, that has a finite length. this notion clear? That this is an infinite set and all its members are, have finite lengths, like set of numbers, set of integers, right? That is an infinite set. Each integer itself is some kind of a finite object. It is, let us say, 10,000, it could be 1 billion, it could be a trillion. So, the number can be arbitrarily large. Similarly, here the strings can be arbitrarily large, but each string in sigma star is finite, right. So, now there is one very, very important notion that we are going to introduce, and that notion is that of a formal language. A formal language L over the alphabet sigma is a subset of sigma star. Okay. This is a formal language L over the alphabet sigma is a subset of sigma star, right. So, sigma star, recall that it has the set of all binary strings over the alphabet sigma, and you take some of them, possibly an infinitely many of them, leaving maybe some out, and that constitutes a formal language over the alphabet sigma. So, it is clear that for this alphabet, for sigma is again binary alphabet 0 1 1 1 0 0 1 0 1 1 1 0 1 0 1 1 1 0, right. This is a set of strings over the alphabet 0 1, and clearly this is a subset of this set sigma star. So, this is a language L. So, we can say that this is an example of a binary language, because all its strings are over the symbol 0 1, and this is of course a finite language, but more interesting would be the example, let us say L 1, let us say x is in 0 1, this is an alphabet, now I am putting the star over it. So, I mean x is a binary string such that x has even number of zeros and even number of ones. How many such strings are there? Clearly infinitely many. At the same time, not all binary strings are in this language L 1. So, L 1 is an example of a language over 0 1, which is infinite, right, but which is not the entire sigma star. So, this language L 1 is a proper subset of, so we can write like this, is a proper subset of sigma star. So, we have introduced a number of terms. Let me just enumerate them and briefly explain once more what each are. Each of these symbols is. So, first of all, we talked of symbols, then we talked of alphabet, right. Then we talked of strings over an alphabet. Then we talked of sigma star for alphabet sigma, and finally we talked of a formal language over sigma. So very quickly, symbols are like 0, 1, these are symbols. Alphabet is set of symbols. So this is an alphabet. String over an alphabet, over this alphabet 1, 1, 0, 1, 0, 1, 1. This is a string, right? Sigma star over this alphabet is the set of all finite binary strings. And a formal language over this alphabet is just a subset of sigma star. L is a subset of, for this particular alphabet, 0, 1. So therefore, L, such a formal language, is also a set which has a number of finite strings in general over the alphabet that we are dealing with. In this case, in this example at least, that alphabet was the binary alphabet. Now, the connection with what we were saying before is this, that we shall be concerned with the set membership problem of formal languages. So now, therefore, our problem is going to be, somebody has some formal language L in mind, and the problem therefore is very concrete. They give me a string and I have to determine whether that string is a member of the formal language. Now, very briefly, although we had said in terms of the graph of a function can be seen as a set, but then what is the justification of talking about or restricting ourselves only to set membership problems of languages? And that is because the idea is really very simple. You see, when you write a program, right, then that program takes some input, and that input is what? Is actually a string, because that input you need to key it in through the keyboard, or maybe it is coming through a file, or whatever it is, you can think of that input to be a string over some alphabet. And the output is again, in general, is of course not yes or no as in the set membership problem, but here we appeal to what we said earlier, because our goal is to show that something cannot be done by programs, and so if that is a function, then if we can show that the corresponding graph, which is going to be in this case going to be basically strings, basically graphs, those graphs of those functions that we are interested in, since our inputs are going to be strings, outputs are going to be strings. So these are going to be pairs of strings themselves can be seen as a string, and therefore it is really a set membership problem where the sets are really sets of strings, and these strings are finite strings, right? I mean, you never, or it doesn't make sense to say that my input is a string which is infinitely long, because such an input you can never even provide to the program completely for that program, your program to work on that input. So, inputs are always finite, and in fact, they are always finite strings in the programming context. So, therefore, this restriction is not something which is very restrictive, right. Although it seems a great restriction, you see, from functions we are coming to set membership, and then again we are saying that we are not interested in all kinds of sets, but only sets which are just sets of strings over finite alphabet. Now, that really is the basic issue in this course, that ultimately, of course, we will be talking about this question of whether certain set membership problem admits an algorithm or not. But we'll come to that goal in a series of steps, if you like. So, what we are going to do is we are going to invert the problem in some sense. We'll think in terms of models of computation. Let me write this down. Right? And that means some abstract way we are saying we will describe a class of algorithms. Okay. And that abstract way, in fact, going to be by specifying what are called automata. See, these are again terms which will be much clearer when we see really examples of and we deal with them. So, our models of computations, let me just say this for the time being, are automata of various kinds. So, it will define a class of automata, and then will ask the question what kinds of set membership problem this class of automata can solve. The kinds of automata that we are going to see, we'll start with a very simple class of automata. They are called finite state automata. Now, even here there will be various kinds, you will see later, deterministic, non-deterministic, and then we will study what kinds of languages for which this model of computation can solve their set membership problem, after which, and this is going to take at least 15-20 lectures, and then we will talk about, in terms of automata, that is going to be push down automata. And again we will study the classes of languages for which push down automata will be adequate to solve their membership problems. And then finally, we will look at the most general class of automata which is possible, and you might have heard of this term. They are called Turing machines. And as we go along, there will be many other things we will study, and for example, we will study the notion of grammars, and here we will study regular grammar, context-free grammar, and we will briefly mention what are context-sensitive grammar, and then finally the unrestricted grammar, and there will be some correspondence with these things that we are going to study. And it is at this point, so as I said, at the almost when we come to the end of the course or in the last part of the course, we are going to encounter set membership problems for which there will be no algorithms to solve. We will stop here, and in the next lecture onwards, we will start with finite state automata first, and we will be dealing with them for quite some time.